Okay, welcome everybody to the latest Trillium Flow Technologies webinar, where we look at valve challenges in power applications, specifically valves applied to Hersing boilers. My name is Simon Bradshaw. I look after engineering for Trillium, and I'm here with my colleagues, Sebastian Vermeulen, Jeff Hager, and David Shaw, who are all product managers with deep technical knowledge of the products in this application. They will be doing the heavy lifting on this webinar. Thanks for taking the time to join us. And with that, let's talk about the parameters for today's webinar. Next slide, please. Okay, so first off, we're going to talk about a little bit about Trillium technologies, flow technologies for a moment. Then we're going to go and talk about our portfolios, specifically the valves that are utilized in this particular application. We're going to cover safety valves from Saracen. We're going to cover a number of different types of valves from Hopkinson's and Atwood and Morrow. And then finally, we're going to follow up with Blakeborough Feedwater control valves. So just as a reminder, you can submit your questions at any time at the Q&A box at the bottom of the Zoom window. So please do that as the presenters go through the topics. We will try to leave time at the end for questions and address as many of them as we can. And this webinar will be available on the Trillium Flow Technologies YouTube site a few days after today. With that, let's go to the next slide, please. Okay. So, quick overview of Trillium Flow Technologies. Our product brands are synonymous with the pump and valve industries. With pump brands that you can see in blue there, we have Begerman, Flowway, Gabionetta, Thermomechanica, Rotajet, Wemco, and WSP. On the valve products, which is what most of you are here to hear about today, we have Atwood and Morrow isolation check valves, auto-torque actuators, Batley butterfly valves, Blakeborough control and choke valves, Hopkinson parallel slide gate and globe valves, Saracen and Sabine safety valves, as well as tricentric triple offset butterfly valves and red point valves. All of these are leading names in the industry. On the right-hand side, you can visualize Trillium's global presence. We have a supply chain that spans the globe and key manufacturing and service centers located in Canada, China, France, India, Italy, South Korea, UK, and USA. We have 21 facilities around the world, plus a global network of third-party sales and authorized service centers. This allows us to tailor the technical and commercial aspects of our products to suit your particular project needs. Next slide, please. This is just a brief overview of the heritage of Trillium, which spans over 190 years. We're not standing still. We continue to innovate and make new products and services for our customers and help their processes become more efficient. Some recent examples of additions to the family, as we mentioned, red point valves joined the Trillium family in 2020, expanding our product and service provision for critical service valves. And in 2022, we were joined by Thermomechanica Pompe, which enhanced our offerings in pumps for the power, water, oil and gas markets, as well as our service portfolio. This provides an extensive network and knowledge base of support and service, not just for Trillium products, but also the equivalent product ranges from other OEMs, and should give you the confidence to utilize Trillium for your next project. With that, I'll hand over to Sebastian, who will take it from here.
Thank you, Simon. So we first propose to have a view of a global overview of a power plant, especially a combined cycle gas power plant. So the idea is not to go in detail, but to present the major functional group and identify the location of our product we are going to talk about today. So the first main section on a combined cycle is the combustion turbine that will provide 2/3 of power that will be provided by the gas turbine. The funny thing is our valve operate here on gas, which is in a common view is not directly associated with power. as power on the other end is associated with steam. So in this combustion gas turbine section, we have mostly on-off globe valve, three-way control and butterfly valve, fuel gas cooling air control valve, but also ASME section 8 pressure relief valve working on gas, liquid, and potentially steam, but not as efficient as ASME 1. In the middle, we have the heat recovery steam generator, which supply 1/3 extra power. So the function is as follow: the waste heat from fuel combustion in the gas turbine is routed to this heat recovery steam generator, HRSG, where it is used to generate additional steam at superheat condition. So on this section, we have 4 major components: economizer, drum superheater, and a water preheater. And each of them has the target is to increase the water temperature. So in the economizer, valve operate on water, but potentially on steam. On the steam drum, the saturated steam is separate from the steam water mixture, and in the superheater, at saturated steam is coming from drum. This steam pass through the system to raise the temperature again beyond the saturated point. So it's a superheated steam, dry steam, before being injected on the turbine. So here you will find most of our valve solution, isolation, check, safety, control, butterfly, and desuperheating. So on the HRSG, you will find ASME1 spring-loaded valve. I will briefly introduce. You will also just at the outlet on the main steam line, you will have the main steam parallel slide gate valve. David will talk about in a few minutes, and a Y stop check valve directly nearby the parallel slide gate valve from HRSG to the turbine that will be presented by Jeff. We also have a Feedwater system, the HP drum flow control valve for main and startup that will be presented by David as well. And at the end, on the steam turbine, you will find also some valve like the code rate check valve that will help to present reverse flow, making sure the steam from the turbine go directly to the heat recovery steam generator. So what are the main customer concerns and how can Trillium help? Of course, we talk about performance, how a product can optimize the overall plant performance for cycling operation, how a control valve can make more efficient your plant. Also, how we can reduce internal leakage, so it directly connects to performance. We talk about leakage internal and external as well. On gas turbine, we will be more concerned by fugitive emission that are part of global warming, but steam is not really concerned. But steam has a direct impact on the efficiency, as it is a money maker. The higher steam rate, the highest efficiency we can reach, and how we can also reduce the TCO, the total cost of ownership, reducing the maintenance cost, minimize the downtime, providing, designing a solution for rapid maintenance. So there is no preference for talking about either isolation and control or safety valve, but because safety is a Trillium DNA, we make the choice to start by safety first. So briefly, for people who are unfamiliar with safety valve, we have 2 major family. It's not spring versus pilot, but it's more a technology associated to ASME code. ASME is split as follow. You have on one hand ASME section 8. Now it has been section has been extended, and ASME created a section 13, even if most of people continue to talk about section 8. So and on the other way, you have ASME section 1, dedicated for power application for steam. Both are normally closed device. The only difference is while the ASME section 8 can keep its closed position for 1 year and wait for maintenance time, and doesn't participate to the plant efficiency. ASME 1 valve has a direct impact on the power plant efficiency, as it helps to control the steam, the money maker. It has to open many times because when you inject gas, you inject coal, you have immediately a steam increase that will be vent release by this ASME section 1. So it's very important for ASME section 1 to operate quickly on a very, very short pressure range from the full opening, what we will call the overpressure, and the full reclosing, what we will call the blowdown down, which is here limited at 4% maximum. So the valve operates between 3% and 4%, which is very, very close compared to ASME section 8, where we have 10%, 7%. And we will review in detail some of technology during this presentation. I miss it, but also the tightness. 97% is very, very high tightness. It's 6% higher than API standard 527, the standard requirement we need to meet. It's as close, it is equivalent to pilot operated efficiency, but with a spring-loaded valve, which is a performance thanks to the disc design. So here we have a set of valves dedicated to address different kind of pressure range. Here we talk about star steam, which is a high pressure safety valve. That's the reason it starts at the 600 class and over. In power, it is common to propose flange, but also butt well connection. So here we can offer both for the highest pressure. And because we address the highest pressure, but also the highest temperature, this one is installed on the superheater. We offer the highest grade C12A F91. In Sarrazin in France, we invest on a specific furnace to better handle the post-weld heat treatment of the C12A, which is recognized as being brittle. And we have complete control of this material. As I mentioned, we have the background, it's very brittle, so we need to pay attention on that. And in terms of quality, it's better to have this control. So let's start by Thermoglide. So Thermoglide system is it's a trademark. It's a slide. It's about graphite, carbon graphite sliding ring. It's a heritage of the nuclear segment. Sarrazin and Sebim are sister brand, sister company, both based in France. Sebim addressed nuclear market, and this technology is a try and tested technology in nuclear for more than 50 years now. This technology is very hard component, help to reduce the number of contact between the internal trim. Here, if I have zoom, you see the graphite ring in red. The ring is sliding and there is no direct contact between the guide, the blue part, and the piston, the orange part, thanks to a very close tolerances, 0.5, no thermal expansion directly as well. It's significantly prevent any sizing, galling, unplanned cost that will be generate unplanned cost and potentially can keep the valve in open position. We will see just after the consequence is the valve stay in open position, how much it represents. It also reduces the number of parts we have to consider. Here we estimate, thanks to this technology, if we consider average valve size, the saving is about $40,000 per valve compared to our competitor, and if we consider the entire valve life cycle. So downtime is minimized, not only because we extended the part life, but also we reduce their quantity. Another point is restricted lift. What does that mean? When you have two different, the valve main function is to open at set pressure and release the capacity. But sometimes we are in a standard industry, so we have a required capacity and we need to make sure we supply a valve that meet exactly the next upper orifice that will generate the right capacity. But this capacity has to be as close as possible to the process. If it is oversized, that will generate some shattering. But so we have to consider the valve section, but we can also reduce the lift to reduce the circumferential area. When I reduce the lift, I also reduce the flow path, so I can derate the valve capacity. Here, both valves, Star Steam and Star Flow V, the sister one for low and medium pressure, are equipped, are certified for full and restricted lift. They have two dedicated certificates on steam application. The benefit is immediate in terms of performance. It's allowed to adjust the sizing to reduce shattering, reduce the maintenance because shattering has a direct negative impact on internal trim, and also Potentially, it's reduce the noise and the build-up back pressure. Build-up back pressure means higher reaction force. Higher reaction force directly drives to larger piping support. That's also as a cost. We don't have the detail of that, but piping support and piping is a major investment compared to the valve itself, especially when it is qualified. What we try to do is to estimate what would happen and what will be the loss in case the valve keep its open position or if we don't use restricted lift. In the market, ASME PTC 4.1 provides such a detailed calculation, and it looks like steam cost will be around about $12,000 per $12 per 1,000 pounds. So if we supply the next upper orifice within applying this restricted lift, we can see here the valve certified capacity will be 166,000 pounds per hour when the required capacity is 110. It is what it is because we have a valve set of 10 orifices and we need here to select the next upper one. So the lower is smaller. So the solution then is to restrict the lift and to stay at close to 110. Here it's 115,000 pounds per hour. So the saving is 21 pounds per hour. Based on this evaluation, $12 for 10 pounds, it represents $617,000 per hour. Of course, safety valve is normally closed, so it's more representative to talk about second, but it's $170 per second, so it's already huge. If for some reason, due to streaking components, the valve stay in open position, we can reach this hour before a maintenance guy arrive, so it would be a real disaster. Blowdown. Blowdown is a function that helps the valve to keep its closed position, but it's part of the valve setting. It's part of thing where our service technician has to do on site, because to adjust the blowdown, we have to make the valve, we have to perform live test. So there is a couple of detail here explaining how our adjustment, but the biggest takeaway is first we have this overlap collar that will have a coarse and major impact on the blowdown adjustment, as the steam here is trapped while the valve is reclosing. That makes the pressure increase. So there is three major adjustments: the overlap collar to have a coarse and major impact on the blowdown, and then we have the standard dual adjusting ring, which is quite common for this design. But the takeaway is the design of this overlap collar is very simple and very robust, and help also our service technician to be more efficient. The last but not the least, the Star Steam, the Star Disc. It's also a trademark. Star Steam is very flexible. It's an alloy 718 with lips. This design is help definitely to keep tightness up to 96% versus standard valve at 90%. It's mainly due to also withstand internal stress when the valve is not in operation. This is a flexible disc. It means it's mainly operate on steam and keep this tightness on steam. So we have thermal dilatation. If you do the same test on air, the valve won't be tight. So if there is any steam valve has to be tested on steam, and the tightness we offer is on steam service. So again, high tightness, better steam trap, and then higher operation and efficiency. That's a major impact. All these parts are completely free. It's very important. If we keep internal stress, any misalignment can generate some leakage. So we pay attention on the complete assembly, and we make sure all the internal trim are free to move to compensate any misalignment on this mechanical structure. We take the opportunity to complete this safety presentation talking about the in-situ testing device, but well, ASME1 safety valves should be first hydro tested. This is why they are supplied with hydro plug, but also why a service technician has to perform final testing on site. So the ASME1 safety valve is ready to be fitted with the auxiliary lift assist device. Our team, of course, is committed to support on the hydro plug removal and functional tests like blowdown adjustment on live steam testing, what we discussed about just before. So now I hand over to David, that represents isolation valve solution.
Okay, thanks, Sebastian.
Welcome.
Next slide. I think we're still on safety valves. Okay, so this section of the presentation is going to be talking about gate valves. And in particular, the more critical gate valve applications that you'll find on the HRSG. So obviously there are many applications where a gate valve is used or can be used. But the benefits that we're going to talk about of the parallel slide valve are particularly applicable to the main steam stop and the feedwater isolation valves. So when people think about gate valves, they usually visualize a wedge gate valve. That's because they are the more common type of gate valves in the market. They're generally classified as commodity items. Quite frequently, they're available from stock. So why would you use a parallel slide valve particularly for higher pressure applications, especially superheated steam, where you can have steam over 580 degrees C or over 1,000 degrees F. So first of all, let's talk about the operating principle of the two types of valve. On the left-hand side, you see a parallel slide valve, and on the right-hand side, for comparison, is the equivalent wedge gate valve. A parallel slide valve operates, as we call it, a position-seated mechanism. So all the actuator is doing is lowering the discs down into the seats, and it's actually the line pressure that's providing the closure force. So you can see the red arrow there. The line pressure is acting on the outlet disc, which forms the seal on the seat. By comparison, a wedge gate valve, it's actually the operator's load. So if it's a manual operator, it's the load you're putting into the hand wheel, into the drive nut, into the stem. Or if it's an electric actuator, it's the force from the actuator that's driving the force down onto the stem, which acts onto the wedge and outwards onto the seats, which provides the seating force. So the benefits of this in terms of the parallel slide valve is that it results in a lower operating force, usually around 20%. That in turn results in less stress in all of the drive components, so on the drive nut, on the stem threads, than the equivalent wedge. And it gives a zero leakage because you've got lapped large flat seating faces on there. The wedge gate, by comparison, most catalogues or publications you see for the wedge gate valves will give an allowable leakage to the MSS SP61 or FCI 70-2. Class 5 is even quoted by some manufacturers. This actually is a control valve standard, not an isolation valve standard. So that gives you an idea of the amount of leakage that the valve actually has when it's new from the factory. Okay, next slide. So another valve that Trillium manufactures in the parallel slide range is called a Venturi design. This is what we see on the left-hand side here. The benefits of this type of design is the smooth flow profile through the eyelet that sits underneath the disc. So you can see there, when the discs are open, there's actually an eyepiece follower moves in between the seats. So that gives a true Venturi flow path through the reduced seat bore. The benefits of this is it reduces the internals of the valve, so it reduces the weight, it reduces the cost, it reduces the required travel. And the other main advantage, it actually protects the internals from any debris or wet steam that the valve might have to might see when the valve's open. So you can see the eyepiece follower actually sits in between the seats, and it fully protects all of the seating faces when the valve is open. By contrast, the wedge gate on the right, you can see there's a large gap between the seats. The flow is disturbed through the when it passes through the seats. There's dead bands and areas of recirculation, and this, in some cases where you've got high velocity steam, can lead to vibration of the valve and the pipeline as well. Next slide. So the main benefit of the parallel slide is when it comes to thermal binding. So thermal binding is a well-recognized phenomenon within the power industry, especially where valves are being cycled from high temperature to low temperature. So this occurs when the valve's isolated when it's hot, and when the valve cools, the entire pressure envelope essentially contracts, forcing the seats to trap the disc, the wedge in place. In most cases, then this can't be opened again until the valve's actually heated up, and it can lead to further issues, again, with the drivetrain, with the drive bush, with the stripping of stem threads, etc., which can all lead to a slower startup or a delayed startup, and delaying the plant starting up on demand. Okay, next slide. And finally, maintenance. So parallel slide valves use flat discs and flat seats, which are easily maintainable. The discs can be removed from the valve and lapped on a lapping machine. So long as you've got smooth flat faces, you know the valve's going to reseat just as it did from the factory. With a wedge gate valve, the wedge is matched during manufacture to the seats. So the wedge has to be returned to service in the same orientation, and you also have to ensure that those angles are maintained throughout the lapping process. And finally, if the valve's actually maintained in line, it's quite difficult to know that that's actually been achieved unless you hydrostatically test the valve again once it's returned to line. So just a summary there: shorter travel, faster operation using the Venturi. Thermal binding is just not possible with a parallel slide valve because all of the internals are free to expand and contract. It's smaller actuator required, a better CV as a result of lower pressure drop because of the smooth flow profile, which also minimizes vibration. It's a zero leakage valve, and it's easier to maintain, which leads to longer and better lasting isolation for the lifetime of the plant, which obviously leads to increased efficiency.
Thank you, David. I'm now going to talk about two check valve options that we offer into the combined cycle plant arena. A reminder that if you have questions, please use the Q&A block at the bottom of the screen to get those questions, and we'll review them at the end of the presentation. Okay, so the Y-stop check valve is typically used in the main steam line. It can also be used in the hot reheat, boiler feed pump discharge, and an economizer inlet stop. It's available in sizes from 6 to 24, pressure classes 15 through 2500 for the main steam line, and the class 600, class 900 for the hot reheat line, typically more in the 18 to 24 inch size. They're provided with butt weld ends, and materials can be cast in the common alloys or forged. Typically, the forged valves are F91. There's a slightly higher cost to the forged valves, but the benefit is the dense, consistent material ends up providing a longer life without maintenance issues downstream. The seats are hard-faced in alloy 21. If it's a grade 91 valve, there are special considerations of butter layering underneath the hard facing to prevent some industry problems that have been experienced in the past. The Y valve has a streamlined body to provide a lower pressure drop, and the valves are designed for high pressure, high temperature, and high flow rates. Next slide. So the Y-step check valve line is available both in body-guided and stem-guided configuration. The body-guided has cast ribs that are hard-faced, and the stem-guided is what's shown here. And typically in that main steam line, what you're looking at is F91 materials, and welding on the base metal comes with its complications both in manufacturing and maintenance in the years of the plant life. So this stem-guided design eliminates those body guide ribs and eliminates all hard facing directly on the body material, which is a benefit in cost in downstream maintenance or further in the life of the valve. The body seat ring is hard-faced in LA21 and is field replaceable with a grade 91 to grade 91 weld. The poppet sleeve provides that guidance for the poppet, and it's replaceable by pulling out a retaining ring, slipping in a new sleeve, and replacing the ring. The stem is hard-faced in chromium carbide to provide a high wear surface for both the poppet guidance and the guidance through the cover bushing and the packing area. This stem-guided arrangement eliminates the equalizing line needed for the body-guided rib style, and it's important to note that in the forged designs, it gives us the flexibility to adjust end-to-end, so you can cut out your heat affected zone in the pipe, which you're welding the valve into, and if you have any other special needs, we can accommodate it with the forged design. These views show the operation of the valve, with starting at the left, with flow flowing from the left to the right. This is the stem down with the actuator pushing the stem, pushing the poppet into the seat. You can completely isolate against forward flow. Then when you're ready to run, you use the actuator to lift the stem up, and the poppet now is free to open. It will isolate against reverse flow. And then in the third view, you have the stem up and forward flow, lifting the poppet up to seat on the bottom end of the stem. And ideally, you'll size the valve so that this is where you operate normally to eliminate any motion of the poppet. Okay, next slide. So taking a look at the advantages of the Y-stop check valve, there's a lower pressure drop than the T-pattern globe. The stop check potentially could replace two valves. Typically in that main steam line, you'd have a requirement for double isolation and a check valve. So that would be two gates and a check. This lets you combine the features into one valve. So you have a gate valve and then the stop check valve to provide both the check function and the isolation function. It's fully maintainable in line. And if you choose to use a motor operator, we have some thermal compensation options that you can use to prevent some quick closing stem expansion issues. Okay, next we'll talk about the swing check valve, which is a slightly different design. This typically is used in the cold reheat check line. It's a free swing check valve. It opens with flow and closes as the flow reduces. They have wide flat metal seats that are easy to lap and maintain over the life of the valve, and they can withstand rapid reverse flow closures without any deformation. The streamline path is helps reduce the pressure drop, and the disc is counterbalanced to approximately 50% of the disc weight. So that lets you open fully at a lower flow rate, but still provides that positive closing moment so that as your flow reduces, the valve will start to close. And the bolted bonnet gives you full access to the internals for maintenance. Looking at the disc assembly, you have a self-aligning disc. So there's a little bit of free play between the disc arm and the disc, and that lets you accommodate any kind of lapping errors during the maintenance cycles, that the disc can move a little bit to accommodate that and still give you a good sealing. There's no disc to body contact. The disc stop contacts the body in the fully open position. And there's positive prevention from the disc and arm separation. That nut is then cross pinned and then peened. So there's nothing for the flow to act on to loosen up that joint. And then there's anti-rotation lugs that provide anti-rotation so the disc can't spin and wear out parts during service. Next slide. So this valve also has a side closing cylinder that is designed to encourage the disc to close Ideally, your plant's going to be up and running for a long time, and if the packing gets hard and dry, it could grab the stem. And so this cylinder makes sure that that's not an issue, and it can pull the valve into the flow stream so that as the flow reverses, it will push the disc to the closed position. Typically, the cylinders are provided with a partial stroke mechanism so that you can test each one periodically. We recommend monthly to make sure that the valve is ready to perform its function should it be needed. The cylinder is not strong enough to hold the disc closed against forward flow to starve the downstream systems. Next slide. So here you see the air cylinder has been de-energized. The piston rod retracts, pulling that disc down into the flow stream. And then as your flow decreases, it will pull it all the way to the seat. All right. Review of the advantages. Again, quick closing, low pressure drop, a robust, reliable design we've used for many, many years in turbine applications, and it's fully replaceable or fully maintainable in line. Typically, we provide this in cast materials. There's also forged versions available for some special applications. And then back to you, David.
Okay, thanks, Jeff. So the next section we're going to talk about control valves, and in particular we're going to focus in on HP feedwater control valves. So obviously there's a lot of applications on the HRSG, but this is one of the more critical in terms of the smooth and efficient running of the system. So why this is particularly challenging, it's because of the essentially two modes of operation that the valve has to undergo, and the vast difference between the two. So during startup, so when the HP drum is being filled, you have a full head pressure from the feedwater pump acting on the inlet of the valve, and then at the outlet of the valve you have the empty steam drum, so almost atmospheric pressure. That large pressure drop can lead to issues with erosion or vibration or control if not properly managed. And the low outlet pressure, again, if the wrong trim is selected, can lead to cavitation. And just to give you an idea of the damage cavitation can do, you can see the image on the right. And this kind of damage can occur in a matter of days, if not hours, at severe cavitating operating conditions. So if we move on to the next slide. So once the HP drum is up to pressure, ideally you have the pressure of the drum closely matched to the discharge pressure of the pump for the efficiency of the system. And obviously the higher the flow of the pump, the more pressure drop is taken across the piping components such as bends, elbows, reducers, any valves in that line. So when you get to the full flow of the pump, there's essentially very little pressure drop left for the control valve. So the desired trim here is completely contrasting the startup conditions. What you actually want is a large capacity valve with very accurate control. Okay, if we move on to the next slide. So there's two real solutions for this application. On many plants, the service is actually split into two different valves. So we have a 30% valve generally, which is a startup valve, and the smaller valve, and it's usually piped in a bypass arrangement around the main valve. And once the desired operating pressure of the HP drum is achieved, control is then passed to the main valve. This requires a split range control logic, similar to what you see at the bottom there, where the startup valve opens up to 30% of the flow. Once the startup valve gets to about 70 or 80%, then the main valve starts to open. And you don't want to pass control to the main valve until it's at least 10 or 15% open. So if we move to the next slide, we see an alternative solution. Oh, sorry, on the 30% valve, because of the high pressure drop, you want a severe service trim. Sorry, if you just move on to the next slide from that. So Trillium's severe service trim you can see on the image in the center. So the flow has to pass through a tortuous flow path. So the pressure drop is broken down into stages. And the net result of that you see on the right-hand side. So the same graph we saw on the previous early slide, you can see in red the single stage trim where the pressure drop's taken in one stage and it drops into the cavitation zone. With a multi-stage trim, which is the blue line, you see that pressure drops taken in smaller stages, so the pressure at no point through the trim actually drops below the vapor pressure. So cavitation is completely eliminated. So that's the 30% valve. If you look at the next slide, we'll look at the requirements for the 100% valve. So typically a drilled hole cage, because you want high capacity through this valve. And this also gives you accurate control of the feed water. So if we go to the next slide, we can see an alternative solution. So some plants are actually specified with a combined valve from startup, or some plants actually upgrade to this further in the life of the plant when issues occur with the control on the split range. And what we can actually do is design a trim which combines the benefits of both of the trims. So typically you would have the extreme trim up to a certain opening, so approximately 30% again. And then above that, you would have a drilled hole cage to give you the benefits of the high capacity. So this valve is capable of handling all of the process conditions or the demands of the feed water valve within one regulator. So moving on to the next slide. Another issue in older plants or plants a couple of years after commission is magnetite. So on the right-hand side there, you can see a severe service trim with very small inlets. And this is actually blocked with magnetite on the inlets. And then if you look at the bottom image there, you can see a sort of cross-section inside the trim. And you can imagine this flow path from the inlet to the outlet easily blocks with magnetite, because you can see the CFD there. In the corners, there's very little flow and very little and generally recirculating flow. So any magnetite can drop out of the fluid at these areas and start to block up in the corners until you lose capacity essentially in your feed water valve. Magnetite itself is a desired makeup in the feed water because it increases efficiency of the plant. So it's formed by using chemicals to increase the pH level of the fluid. And these chemicals are also used to reduce the oxygen and reduce corrosion in the boiler. But on the flip side of that, you've passed the challenge then onto the control valve. Okay, next slide. So Trillium solution to this, we've been supplying this solution to a number of plants for around about the last 15 years. Again, utilizing the extreme trim. We've seen how the extreme operates in the same manner as any multi-stage trim, so it breaks down the pressure into stages. But the unique feature of this trim really is the flow profile. So we're not using right angle turns. We're using a smooth flow path from the inlet to the outlet. So you can see the CFD image on the bottom right there. Essentially, there are very few dead areas or areas of recirculation, and the flow paths expand from the inlet to the outlet. So in theory, any debris or magnetite that enters the trim can pass to the outside. And you can see there an image of a valve that's been operating for over a year in service, and there's very little magnetite buildup. The other area on this trim, different to other severe service trims, is the actual inlets to the trim. You don't have the same small areas that are liable to block, and that's because of the pressure distribution across the trim. We don't start with a very high pressure drop across the first stage. We distribute it across the first 4 or 5 stages, then start to reduce the pressure drop. So we avoid the small inlets. And just to point out that this solution is available as well to retrofit to existing valves. So when we move on to the summary of the benefits of everything we've talked about. So we've tried to focus on the main topics of no leakage, ease of maintenance, and overall performance. And the reason for that is essentially keeping the power plant up and running, reducing downtime, and maintaining reliable startups, and reducing the loss of steam. And we've seen those. We've seen the features of multiple valve designs and how they've achieved that. So in the safety valve, we've seen restricted lift, which reduces steam leakage and reduces the use of steam. We've seen a reduced risk of jamming in the Y-stop, the parallel slide, and the check valve. We've seen some of the products that have a reduced pressure drop potentially in the steam lines, such as the parallel slide and the Y-stop. And we've seen the benefits of the extreme trim, potentially reducing maintenance especially on services with magnetite. Okay, so we now have time for questions.
Yeah, thanks, David. So thanks to Sebastian, Jeff, and David for the detailed technical summaries. Just a reminder, we're going to cover the questions now. There is still a little bit time left. If you have a question, please type it in the Q&A box at the bottom. So the first question, the questioner is asking about the name or type of the trim of the combined valve in high pressure feed. I don't know if you can answer that, David.
Yeah, so we still refer to it as the extreme trim, but we actually call it a vary stage, and that's because we're varying the stages within the trim. And just to point out that we can actually characterize this trim to meet the process requirements. So it might not just be the two operating conditions. We can characterize it for any operating conditions in between as well. So we could have more stages at the bottom for the startup cases, and then we can maintain the extreme but with less stages. So where you might have a lower pressure drop and then moving on to the multi-flow as well.
All right, thanks for that. So the next question is regarding safety valves, and the questioner asks, why should we use a lever with our safety valve? Sebastian, you want to take that?
Yes. Well, first, because it is mandatory by code. The code, as the ASME code, required lever for any compressible fluid, gas, steam, and hot water as well. It's very, of course, the lever cannot open the valve. You cannot just handling the lever open the safety valve. 75% has to come from the pressure, the installed pressure on the piping. The lever is only designed to supply the 25% remaining, mainly in case of urgency. It's a safety product, operate mechanically. If for some reason the internal trim is blocked, we have to supply a lever to unlock the trim. Safety is the last barrier to protect pressure equipment, whatever it is. So that's the ultimate barrier, the human barrier, to prevent any blockage.
All right, thanks, Sebastian. Next question is also about safety valves, and the questioner asks, regarding safety valves, do you adapt the spring material depending on the relieving temperature?
Yes, as well. Of course, we adapt the material, but on steam. Steam is steam. It's a well-known process, so it's not a big challenge for steam application, especially on ASME1 valve, because the spring is vented. So we adapt the material depending on the temperature, but spring is vented bonnet. It's particularity of ASME1 is the spring is at atmosphere directly. So we don't have a big challenge, but for ASME section 8, where we have some corrosive application, of course, we adapt the spring material. It can be Inconair, it can be Monair. It depends. But for ASME1, because steam is steam, mainly it's a carbon and a stainless steel.
Okay, thanks, Sebastian. The next question is regarding parallel slide gate valves. And the questioner asks, what are the intangible savings in using a parallel slide gate valve? Do you want to take that, David?
Yeah, so really the savings come down to the maintenance period and the leakage, so the maintained shut-off over longer durations. So initially you might get an equivalent performance, but over time, after the valve's been maintained several times and the seats have had to be relapped, then you still get that almost guaranteed shut-off with a parallel slide valve, which obviously reduces unwanted steam leakage in the process and increases efficiency.
Okay, yeah, thanks for that, David. Next question we have up is regarding the pressure safety valve, and the question asks regarding a section 8 valve. There are 2 holes in the guide. Could you advise the function of both of those holes? I think they may have confused it with the other pipe, Sebastian, because that's the one you were showing, but could you take that?
Yeah, I think, the hole, first, because on ASME section 8, we have one single adjusting ring on the body, and the second hole is to have a drain, because
maybe you could put up the slide, just perhaps maybe it would be beneficial to put up the slide while you're talking.
Yeah, but okay, let me get back to this slide.
Let's see if we can help the questioner out here.
Yeah, I cannot jump. Okay, I will. So here we can see, I think,
maybe slide
the 2
19.
hole, slide 19.
Try that one.
Quite the same, but yes, here we have 2 hole, but in reality we have 3 hole, because we always have 2 hole to first place the upper adjusting screw and lower adjusting screw, and we have 1 additional hole for the vent, for the drain. So on ASME 1 we have 3 hole total because we have 2 locking nuts, locking screw, sorry. And on ASME section 8, on the right bottom side, we don't have this upper adjusting ring here. So this is not doesn't exist. So that's the reason we have only 1 single adjusting ring and adjusting screw, and plus 1 hole for the vent, for the drain.
Is that adjusting screw to adjust the blowdown?
Exactly, yes.
Yeah.
That's it's more than that. It's I think, we explain it here. Each screw has its own function. If I move up the lower adjusting ring, I will have a sharp opening. What I want, because again, we talk about performance, but safety is the first function of safety valve is to ensure safety. It means to open at set pressure and reach the right capacity. So it's very important to reach the right lift, to reach the right capacity. So it's better to have a sharp opening and a long blowdown, even if blowdown is performance. So the idea of this ring is to find the right compromise. It's not black and white. It needs to be adjusted carefully to have the right compromise between the full opening and reach the right blowdown performance.
All right, thanks guys. I think maybe we can sneak in one more question. The question asks, can magnetite also damage other parts of the trim, such as the plug and cage?
Yeah, and that's a very good point as well. We didn't really talk about the shut-off capability of the feedwater valve, but it is important that the feedwater valve actually maintains a tight shut-off. And that's because during startup, the feedwater valves are closed and the flow from the boiler feedwater pumps recycled through a minimum flow valve. So in these operating cases, you get a high inlet pressure to the valve when it's closed, and obviously a low downstream pressure. And any leakage across the valve obviously loses efficiency, but it can also lead to further damage of the seating. So the magnetite itself is very hard crystals, and it obviously at high velocity through the trim that could damage the plug and seat sealing faces. So to overcome that, we would usually use a either hardened trim materials or hard facing such as Coleman 5 in feedwater applications. And we also have protected seating face options where that's been known to be an issue on site.
All right.
So especially when we're talking about existing valves and improving performance and upgrading, there are a number of options and features we can incorporate into the design.
Yeah. All right. So we're at time. Thanks to our three presenters who spent a great deal of time putting this technical presentation together: Sebastian, Jeff, and David. As we mentioned at the beginning, and there was a question on it, this presentation or webinar will be available to view on the Trillium Flow Technologies YouTube site in a few days. So you can watch it again at your leisure or download it, whatever. And with that, we'll finish the webinar. Thank you very much for attending. We appreciate your time in doing so. Thank you and good day.
Thank you.
Thank you very much, everybody.
Thank you.
All right.
Bye.